Hi everyone, welcome back another session of electronic device. In this session, we are going to discuss about the coupled diode model of BJT. It's known as Ebers-Moll model as well. Please take one paper and pen and note down the equations which I am explaining in this, because equations looks very huge. If you simply watch and go this video, nothing going to get from the video. It's very difficult to understand one step to next step if you are not writing the equations. Once you write and follow the step properly, it's very easy to understand and very easy to write in the exam point of view as well. Okay, let's start. So here we need to consider two mode of BJT. One is known as normal active mode, another is known as inverted mode. There is one more mode that will be explained using these two modes only later. So normal active mode is meant by the emitter junction is forward bias and the collector junction is reversed bias. So we have a PNP transistor. We have a PNP transistor, right? PNP transistor. So normal active mode means PN junction, this is my emitter junction, this is my emitter junction, this is my collector junction. Emitter junction and this is my collector junction. So these two junctions we already seen in previous video. This junction supposed to be forward bias and this junction supposed to be reverse bias. If I maintain that biasing condition to the BJT, on the BJT, that mode is known as normal active mode. Okay, what is inverted mode? If I invert the biasing condition, that means PNP, the emitter junction is reversed bias and collector junction is forward bias. Okay, that is known as inverted mode. So for time being, you just understand we are going to explain in deep about these two mode. So in normal active mode means emitter junction is forward bias and collector junction is reverse bias. Inverted mode means emitter junction is reversed bias and the collector junction is forward bias. In some application, both the junctions are forward bias. Some of the applications. Okay. Like switching of transistor, we need to bias both junction forward. Let's discuss later, it's there in the syllabus. Okay. So what we are going to do in this session, develop a general approach for both cases, or I can say all three cases. Okay. So initially we start with the normal active mode. Let's see what is normal active mode. Yeah. Look at this big diagram and you could see PNP transistor here and this is my emitter junction, no doubt. This is my collector junction. Collector junction. Okay, so look at this polarity of the battery. Okay, I could make out this is forward biased and this is reverse biased. Okay, and look at this one small diagram here, and once I applied this biasing condition to these two junctions, we know that the holes are going to inject from highly doped P region. Okay, purposefully I am not taking the term emitter, collector and base for explaining the normal mode, reverse mode, and throughout this Ebers-Moll explanations. Okay, you will come to know later why. So the holes are injecting from highly doped P plus region, that is my emitter only. Okay, so what will happen? Holes are injected here. Okay, and this we know this length is less than the diffusion length and it reaches the P region. So I should take one parameter, that delta PE. Delta PE is nothing but the excess hole concentration at the edge of the emitter depletion region. So this is my width. Okay, W, the base width is W. This is the point where I can mark W is equal to 0, and this is the point where I come W is equal to WB. Okay, here my base starts, that it starts from 0, the length is WB, the total length is WB. At the point W is equal to 0, what is the concentration of hole? Definitely more number of holes are injecting from highly doped P material, right? So here definitely this region I can see more number of holes. Then holes are started diffusing slowly and reaches the transition region here, and it is taken towards the collector region. So this moderately doped P region is going to collect the holes. So here you can see, if I consider delta PE is the concentration of hole at this point, so the concentration will be high. Okay, so delta PE is nothing but change of holes. Okay, so delta P, the small amount of holes. So that is actually more here, right? As we move on this direction, the concentration will reduce. But once we reach over here, what will happen? As soon as the hole reaches this point, it will that hole will move suddenly towards this region because of the electric field. So if I look at this region, the hole concentration literally 0, because as soon as the hole comes this point, I mean W is equal to WB, the hole going to drag towards the collector. So if I draw a diagram like this is actually the change of holes inside the base, and xn is the axis distance, and if I take here, you can see this diagram corresponds to this. Okay, so hole concentration is more here and the hole concentration is 0 at this point. That's what the diagram, this graph says. And there will be a current when holes are moving, there will be a current. This current is actually emitter current when we apply a normal active mode. That is why I mentioned IEN. And look at this junction, definitely there will be a whole movement across the junction. But when you look at this area, you cannot see any hole concentration, because as soon as the hole comes this point, that will taken into this collector region. So the concentration will not be there. That means the hole will not accumulated here as compared to the hole accumulation at this point. Here the accumulation of hole is more, and when I travel towards the collector, the hole concentration gradually reduce, and at this point the concentration of hole is literally 0, because holes will not maintain here. It will taken into the other side immediately. So again there is a current across the junction, that is actually collector current in normal active mode. That's why represented ICN. IEN is the emitter current at a normal active mode. ICN is the collector current normal active mode. So I hope you understand about this diagram. Okay. So remember 3 terms. Delta PE is the excess hole concentration at the edge of the emitter depletion region, and IEN is the emitter current at the normal active mode, and ICN is the collector current at a normal active mode. So that's about normal active mode. Don't forget this diagram, we need it later. And see the inverted mode. The emitter junction is reverse biased and the collector junction is forward biased. Look at this diagram. Okay, this is my still this is my emitter only. Still this is my emitter. Okay, this is my collector. This is base. No doubt in that. But what I did here, this collector junction is forward bias and this emitter junction is reverse bias. Then the whole injection takes place from moderately doped p-type material. Okay, moderately doped p-type material. This is collector only. This is our collector only. We not going to change the name of this portion, but I have biased ulta, reverse, inverted mode. Okay, the hole will transfer from moderately doped P region and it reaches the base n-type material. Everything remains same. The hole will diffuse, and as soon as it reaches at this point, and it will drag towards the highly doped p-type area. So emitter is going to collect the holes which is being injected by the moderately doped p-type area, that is a collector. Okay, here the delta PC is actually the excess hole concentration at the edge of the collector depletion. Here also we can take it that this is a W is equal to 0 and this is W is equal to WB. Where will be the hole, where we can see the more hole concentration? The hole concentration will be more in this area because holes are injecting from the collector. Okay, if I look at this point, the concentration of hole will not be available because as soon as the hole reaches near to this transition region, that is going to drag across this junction and reaches my emitter. Okay, don't confuse. In previous diagram, my emitter is actually injecting the hole and collector is collecting the hole, and in inverted mode my collector is injecting the hole and emitter is actually collecting the hole. So the operation is inverted. And see, the current direction is like this, definitely no doubt, but here there will be current, that is a collector current only, but I have taken in this direction, so this is supposed to be minus. So wherever I take the collector current in the inverted mode, I should maintain a negative sign. And here also we could see the current direction is from right to left. So here I mentioned left to right, so this will be minus IE. Okay. So we will maintain the negative sign in all the expressions. So no need to mention the negative here. You should keep remember that even if the direction mentioned from left to right, actual current flowing from right to left in inverted mode. Okay, here IEI emitter current in inverted mode is the emitter current at the inverted mode. ICI is the collector current at inverted. That's what I stands for. Before it was IEN, emitter current in normal active mode. Here it is IEI, emitter current in inverted mode. The whole concentration will be huge when W is equal to W, where W is equal to WB. Okay, whole concentration literally 0 at W is equal to 0. That's what I mentioned here. But when we compared with the previous diagram, okay, the concentration of hole here will be less compared to the previous one, because here this region is highly doped. So more number of holes will come here. This is moderately doped, so that the concentration will be less. So when I compare this, look at this, this is for normal active mode, this is a inverted mode. Okay. In third one, if emitter and collector junctions are forward bias, both the junctions are forward bias, no need to explain with the diagram. In this diagram, emitter junction is forward bias, and in this diagram, collector junction is forward bias. I am going to superimpose these two diagrams. I will get both junctions are forward bias. So my whole concentration at emitter side where W is equal to 0 is delta PE, and the whole concentration at the collector junction where W is equal to WB, I'll get this. So, and there will be two currents flowing through the junction. Okay, when I superimpose these two, IEN by IE, so where total IE, total emitter current will be sum of these two, algebraic sum of these two, that is IEN plus IEI. Okay, then the total current IC is equal to ICN plus ICI. No doubt in that. When we superimpose these two diagrams, the diagram look like this. This is almost equivalent to both junctions are forward bias. Okay, now that is the meaning of this. That is actually normal active mode and inverted mode. Okay, now I am going to find out equation for IEN, ICN, IEI, ICI, and I am going to find out what is IE by adding these two, IC by adding these two. That is actually the Ebers-Moll equations. Okay, so before I go to that slide, I want to recall the previous class information. You may be remembering the diode current. Okay, you may be remembering the diode equations. I is equal to I0 into e to the power QV KT minus 1. You may be remembering these expressions. In last module we have learned it. This is diode expressions, diode current. Okay, so I am making use of these equations and I am writing the equation for this PN junction. This is basically PN junction. If I consider only this is a diode, and I am applying forward bias to the diode. So definitely there will be a diode current across this junction. Okay, since it is BJT, since we call it as emitter junction, I should also include that into the expression. So here the current flow through here, it's IEN, right? This is basically a diode current only, right? The diode current expression, using this expression I am writing expression for IEN. So here there will be a reverse saturation current, that is reverse emitter saturation current, reverse saturation. This is I0 reverse saturation current, that I am just replacing using the expression IES. IES nothing but the emitter saturation current in the normal mode, and the voltage is representing VEB. I am applying the voltage between emitter and base, so that's QV by KT by minus 1, This V, especially because we have a 2 source over here, right? So representing with the QEB. So IEN, emitter current in the normal active mode, is equal to IES, emitter saturation current, into e to the power Q VEB by KT minus 1, and we know that the excess hole concentration at W is equal to WB will be 0. That means the excess hole concentration at the collector junction is 0. Okay, and we have learned one more expression in previous class. IC is equal to delta IE. So let's take a current transfer ratio alpha, okay, which represent the emitter to current amplification. So we learned it in previous classes. So using that expression, I can write expression for IC. What is IC is equal to alpha IE, and we learned this is actually less than 1. So IC is almost equal to I. The ideal case is alpha is equal to 1. Okay. So that we get IC is equal to IE. So using this expression, I am going to write the collector current in the normal active mode. So look at this ICN. So this IEN I have written using the diode current expression. Okay. So since we have a collector junction and two junctions over here, I should specify it. So reverse saturation current, emitter saturation current, IES. Okay. So this is the expression for emitter current, normal active mode. The collector current can be found out using this current transfer ratio, using the current transfer ratio expression. ICN is equal to alpha N. Alpha N means, alpha N means current transfer ratio in normal mode into emitter current. So I just substituted the expression. I am getting ICN is equal to alpha N IES into Q to the power Q, e to the power QVEB by KT minus 1. So don't confuse these two expressions we got. What are the expression? We got IEN expression and ICN expression. So next we need to find out expression for IEI, right? Emitter current in inverted mode and collector current in inverted mode. Let's see that. So look at this diagram. This is inverted mode. This junction is forward biased and this junction is reverse biased, right? And delta PE is equal to 0 in this case. So here we have to write expression for the collector current, even if this is emitter only, phase only, collector only. So but we are applying a inverted biasing configuration. So whatever the current flow through this collector junction, I should mention IC only, right? So IC is equal to ICS. What is ICS? Collector saturation current, magnitude of collector saturation current into e to the power QVCB, right? QVCB, this is CB, I applied the voltage CB by KT minus 1. Okay, why do I mention minus? If I mention minus, the current flow is in this direction. So in previous way, if I consider the current direction is in previous normal inverted mode, normal active mode, current direction is like this. So here it is opposite that, that's why I took a minus symbol over here, right? And similar way, I can find out here IC, I is written over here, and next I find out IEI. Since it is reverse bias, I can use the current transfer ratio here also, but in previous case my expression is IC is equal to alpha IE, but in this expression is IE is equal to alpha IC. Okay, here I should mention N, here I should mention I. Okay, so whatever the current flow through this junction should be alpha time greater than whatever the current flow through this junction, because this is reverse bias and this is forward bias. Okay, so look at this one. IEI is equal to alpha I into ICI equal to minus, because this minus I should mention over here, minus alpha I into ICS e to the power q VCB kt by 1. So now I have expression for current, emitter current in normal mode, collector current in normal mode, and emitter current in inverted mode, and collector current in inverted mode. Then how do I find out? When I superimpose these two, superposition, if I apply superposition to these current, my IE is equal to IEN plus IEI, and my IC is equal to ICN plus ICI. So I added these two expressions. IE is equal to IES into Q e to the power Q VEB by KT minus 1. So that negative sign is there now, that I have taken here, alpha I into ICS into e to the power Q VCB by KT minus 1. That is my emitter current. That means the current flow through the emitter junction. That is known as emitter current. Next, IC, the current flow through the collector junction. Doesn't matter whether the junction is forward biased or reverse biased. Okay, in both cases we are considering when we apply the superposition to these two conditions. So here IC, look at this, IC is equal to ICN plus ICI. This is expression. Okay, ICN equal to alpha n IES into q to the power q e to the power q VEB by KT minus 1 minus ICS into e to the power q CB by KT minus 1. So this equation is known as Ebers-Moll equation. Ebers-Moll equation. So using this expression we are going to model our BJT. Okay, so when we model our BJT, look at, this is actually the diode current. This is a diode current. So this I can represent using a diode exactly. This is actually the current. So these two things I supposed to mention using the current source. This is a current. Alpha into ICS is a IE. Alpha into IES is equal to IC. Right. So I need to mention using current source, and these two I need to mention using the diode. Okay. For that, a slight changes we need to make. So we know these two expressions before only. Excess concentration delta PE is equal to Pn. What is this Pn? Minority charge carriers in the base. Okay, holes in the base. Okay, what is delta PC? Minority charge carriers in the base. So this is EB, this is CB. We are applying voltage between emitter and base here, and the collector side we are applying collector and base. So we have these two equation. From this equation I am finding out delta PE by Pn, and look at this, delta PC by Pn, look at this. So we have this expression before, and this is going to replace with this expression, and this is going to replace with this expression for simplification. Now I get this. Similar way in this expression also, q e to the power q VEB by KT minus 1 replaced by the same expression delta PEI by Pn, and this expression is replaced by delta PC by Pn. So I will be getting these two expressions. So finally my IE is equal to IES into delta PE by Pn minus alpha I ICS into delta PC by Pn, and my collector current is equal to alpha N IES into delta PE by Pn minus ICS into delta PE by Pn. Okay, using these two expressions I am going to draw the Ebers-Moll model. So IE is equal, this is my, I told you before, this is actually expressions of diode, this is again expression of diode, this is expression for expression of current, and this is another expression of current. So I need to maintain diode for these two expressions and current source for these two expressions. Okay, so this is actually Ebers-Moll model. So IE is basically IES delta PE by Pn. Opposite that, this I have taken a positive and this will be minus, plus. Okay, plus means the direction is opposite. So plus minus alpha I CS delta PC by. Okay, so that is a common term I will get here. Here if I see, I will get this term. Okay, and IC is similar way. Alpha N IES delta PE by P is a positive, so is towards this direction, but this is in negative, so I should maintain this direction. So if I look at, if I take the here, this plus the term which is available here plus the term available here. So I will get IE and IC separately. And what will be the IB? That you have to do it. For that, IB is equal to IE minus IC. Using this expression, if you do IB is equal to IC minus, you subtract IC from IE, will be getting IB, that is actually this expression. So now we have modeled our BJT using Ebers-Moll expression. Any doubt? Yeah. Okay. So we are again going to simplify this expression. Look at this. This is my Ebers-Moll equation. I have named as equation number 1 and equation number 2. What I am doing is multiplying equation number 1. That means what I am doing, multiplying equation number 1 with alpha n. Okay, that equation I am calling as equation number 3. Okay, and subtract equation number 3 from 1. Okay, if I do that, if I am multiplying equation number 1 with alpha n, that is I am multiplying alpha n for this expression, alpha n IE is equal to alpha n IES e to the power q VB e by KT minus 1 minus alpha n alpha I ICS e to the power q V CB by KT minus 1. Okay, third equation. Next I am going to subtract this equation number 3 from equation number 2, not 1, equation number 2. Equation number 2. If I do that, I'll get like this. Just let me erase this. This is nothing but 2 minus 3. So equation number 2, IC minus alpha n I, and this is expression, this is the same expression, and ICS, I draw this complete expression with the one color, and minus IE. This entire expression is here. Okay, alpha n IES and the exponential term, right? So this minus will become positive, no doubt in that. Alpha n, alpha I, ICS. So look at this here. Let us find out, is there any common term? This will cancel each other. So this term will cancel each other, right? This term and this term will cancel each other, correct? Yes, cancel each other. Then finally we will get only this IC minus alpha n IE, will get these two term only. Okay, alpha n alpha I ICS QCB by KT minus 1 and these two term. Okay, and the next, yeah, this is the term we have. From here you can see this ICS, this is a common, I am going to take outside. Okay, I am going to take outside, minus ICS into e to the power QCB by KT I am taking outside. What I am going to take outside? Minus ICS e to the power QVCB by KT minus 1. This I am going to take outside. So I will be getting like this. So IC is equal to this expression. Okay. Similar way, next what I do, equation number 2 multiplied by alpha I and subtract the resulting expression from 1. Finally I will get this. So I got two expressions, and again I am going to simplify the term. What term? This term I am going to represent it by ICO, and this term I am going to represent it by IEO. If that is the case, my final expression of IC is equal to alpha n I. So this entire term become ICO minus ICO into e to the power, that exponential term, and IE alpha ICI, this entire term represented by IEO. So if I draw the Ebers-Moll model of this one, I will get like this. Okay, so my IE is equal to alpha I CI current, and this is diode. Okay, this is again diode reverse, and alpha n I is positive. So it's supposed to be in there. So when we compare this diagram and that diagram, this before it was in opposite, this is other direction. Okay, so if I again we can reduce it again. So we are going to stop reducing the expression here. Okay, so this is how I represent my BJT if I apply normal active mode, inverted mode, and if it is a superimposition of both cases, that equivalent diagram look like this. That is Ebers-Moll model, Ebers-Moll equations. So guys, equations are very simple to remember. Only you need to remember 2-3 equations initially. Remaining all the equation you can derive, no doubt. Okay, if you go through step by step slowly, it will be very easy to learn. Okay, thank you.